So for the next session, I welcome you all. It's our great honor to introduce our distinguished speaker for the next session. It will be Dr. R. Karunanithi, Associate Professor in the Department of Aerospace Engineering from B.S.Abdur Crescent Institute of Science and Technology. Dr. Karunanithi sir holds a PhD in Metallurgical and Materials Engineering from NIT Durgapur and a ME in Production Engineering from Annamalai University and a BE in Mechanical Engineering from Bharatdas University. With over 2 decades of academic and research experience, he brings a rich blend of teaching, research, and industrial exposure. His research focuses on material characterization, powder metallurgy, metal matrix composite, corrosion, and tribology engineering, and biomaterials. He has guided several PhD scholars to completion and currently supervises ongoing work in advanced composites. Dr. Karunanithi sir has been principal investigator on prestigious projects funded by SERB at the Ministry of Education, Saudi Arabia, with research grants over 70 lakhs. His contribution have been widely recognized through publications in reputed journals. He also represented India at many international conferences, including recently in Sweden and Hyderabad, and has delivered expert lectures in FDPs and various workshops across many institutions. So let us a warm welcome to Dr. R. Karunanithi sir and look forward to gain valuable insights from his session today. Sir, please, sir.
Good evening to one and all. Thank you for your nice introduction, Dr. Dinesh Babu sir. So today I am going to present the synthesis and characterization of hybrid nano Al₂O₃ Y₂O₃ dispersed aluminum alloy 7017 alloy by mechanical alloying followed by hot processing techniques. Okay, one of my research scholar did this work. So today I am going to deliver this the topic. This material is used in ballistic performance applications. So the outline of the presentations, introduction, literature review, the research gap, objectives, work plan, experimental procedure, results and discussion, conclusion, and scope for the future work, and publications and references. So the powder, this topic is fully focused on the powder metallurgical fabrication methods. What is meant by powder metallurgy? This is the powder metallurgy means the elemental powders, mixing of the powders for blending, and then compaction. In the compaction techniques, there are different ways: spark plug sintering, cold pressing, and hot pressing techniques like that. Several fabrications techniques, and also the sintering mechanisms, and followed by cold uniaxial compaction or hot pressing, cold isostatic pressing like that, then followed by the sintering process like laser sintering, spark plasma sintering, and conventional sintering process like that, different processing parameters. Then finally we'll get the final product, and also we are going for the secondary operations like extrusion like that, then we'll get the finished products. In this powder metallurgical process, we can able to make a small component also, like in our watch, we can make the small gears also possible to make. So this is the simple process in the powder metallurgical process. So we used in mechanical alloying methods. So the phenomena of nanostructured formation by mechanical alloying. This mechanical alloying during the process, the main function is repeated fracturing, deformation, cold welding, and occurs the collision between the balls to powder and a high impact on the powders. So this is the tungsten carbide balls and vials. We used here 10 diameter of the balls, and we used here the processing control agent. We are used as the toluene. So in between the ball and powder collisions, the particles get reduced in micro level to nano levels. So by using these methods, we are converting the powders from micron level to nano level by through the mechanical alloying methods, mechanical alloying or mechanical milling methods. So these are all the some of the literature surveys we did. We chosen the matrix material for aluminum 7017 17 alloy. This is basically aluminum, zinc, magnesium, copper alloys. They did the alloy samples fabricated by powder metallurgical routes at various stages of the milling. They did the peaks like aluminum, zinc, magnesium, which new peaks corresponding to the solid solutions like aluminum, zinc, magnesium alloys, Mg, Z, and 2, like that we'll get. This aluminum 7075 alloy with tungsten carbide composites. So based on this material, they have chosen the powder metallurgical routes. And also they found the various structural parameters such as crystal size, lattice strain, dislocation density, and lattice parameter of the milled and sintered products. And aluminum 7075 alloy related this again the powder metallurgical route. The microstructure observed the flake-like powder structure and hardness was increased from 101 BHN to 108 BHN. Okay. So the hardness value was improved due to this mechanical alloying methods. And another one more literature 7017 aluminum alloy was purchased from the DMRL as the thick plate of 10 mm. Then they did the heat treatment study like the samples were artificially quenched and heat treated at underage, peak age, and overage conditions like T4 is the underage, then T6 is the peak age, and T7 is the overage conditions. They did the heat treatment process, then they were characterized the different techniques like scanning electron microscope, TM, and DSE were examined. Then the mechanical properties, they found the hardness and tensile strength have been analyzed for the different heat treated process. And the one more, the literature survey aluminum 7017 alloy, this DMRL thick plate 30 mm, the plate were hot rolled at 1100 degrees Celsius and reduced the plate at 8 mm thickness. The heat treated and tempering was done on the plate 200 degrees Celsius and 600. So mainly the mechanical strength have been improved due to this heat treatment process. In this work, the research gap were identified from the literature survey, synthesis, and characterization of the nanocrystalline aluminum 7017 alloy reinforced with hybrid nano composite like aluminum oxide and yttrium oxide prepared by the mechanical alloying method, followed by the hot processing technique. This is the research gap was found from this based on the literature survey. So the objectives of this work is to investigate the role of mechanical alloying and hot pressing techniques towards the development of hybrid nanocomposites. This material is particularly used for in ballistic performance applications. Initially, we decided 4 set of materials such that one is the matrix materials like aluminum 7017 alloy, and then the aluminum 7017 alloy with 10 volume percentage of Al₂O₃, and one more thing, another one composites like aluminum 7017 alloy plus 10 volume percentage of yttrium oxide. Systematically we analyzed, then we gone for this, we prepared for the hybrid composite aluminum 7017 alloy plus 10 volume percentage of aluminum oxide and yttrium oxides. So we meticulously prepared and characterization of these all the synthesized composites using the advanced microscope techniques for microstructure and EDS analysis and XRD analysis to perform to study the phase evaluation of the materials. So the mechanical properties like the hardness, compressive strength have been investigated, and also the various strengthening mechanisms such as solid solution, grain boundary strengthening, dislocation strengthening, precipitate and organ strengthening mechanism have been illustrated by numerical equation. This is the methodology we followed. The material selection for aluminum 7017 alloy. This is particularly aluminum, zinc, magnesium alloys with the chemical compositions. Later I will explain. And the reinforcement we have chosen as the Al₂O₃ and yttrium oxides. The processing method is the mechanical alloying for different milling time duration like 5 hours, 10, 20 hours, up to we milled for the 20 hours. Then characterization of these milled powders by using the X-ray diffraction analysis and high resolution scanning electron microscope and high resolution transmission electron microscope and DSC thermal scanning, thermogravity and the differential scanning colorimetry analysis. We did the powder characterization. Then followed by the prepared samples, powder samples, we compacted the hot pressing techniques. In the hot pressing techniques, we used uniaxial compaction with heating rate of 400 degrees Celsius, applied pressure of 500 megapascal and holding time of 1 hour. We used for the hot compaction. Then the prepared specimens were tested for the mechanical behavior of the samples. We measured the density of the sample, hardness, and compression test. Then characterization of the compacted samples like X-ray diffraction analysis and high resolution scanning electron microscope and high resolution transmission electron microscope. So this is the matrix material chemical composition. We used aluminum 91.0185%, zinc 5.2%, magnesium 2.3, copper 0.12%. This is the chemical composition of this aluminum 7017 alloy. So this is the methods we followed, the methodology. This is the aluminum 7017 alloy. This is the aluminum oxide and yttrium oxide. We blended these powders. Then this is the blended powders. Here we are used the mechanical alloying methods. We used ball to powder ratio 10:1. Then the speed ratio of 300 RPM. We are used as the toluene as the wet medium we used, and also the rotation of the speed 300 RPM. We used in the mechanical alloying methods by wet milling methods. Then we compacted these powders. We are taken as the uniaxial compaction, and we followed by this. This is the upper punch. This is the lower punch. This is the heating element. This is the thermocouple. So we prepared the characterization purpose for these samples for 10 mm diameter and a height of 5 mm. We prepared for the compacted samples. Then by using the uniaxial testing machine, then we followed by the mechanical characterizations. So this is the methodology we followed. The results and discussion. First, we'll discuss about the matrix material, study on the synthesis characterization and mechanical behavior of this nanocrystalline aluminum 7017 alloy, prepared by mechanical alloying, and HPT means hot pressing techniques. So we based on these mechanically milled powders, we measure the time interval of this 0, 5, 10, 15 and 20 hours. We used 1 hour milling time, means we are given 1 hour rest for every continuous time period of this mechanical alloying methods. Then we measure the particle size by using the Melvin particle size analyzer. If the milling hours increases, the particle size was reduced. As the milling hours in 20 hours, this one is the 20 hours. In the blue color shows the 20 hours, the particle size was below 15 nanometers. So the structural evaluation of these powders, mechanical alloyed powders, and hot pressed process samples were characterized. The structural changes like severe plastic deformation of this SPT, severe plastic deformation of the powder particles during the mechanical alloying process can lead to grain refining and variation in the crystal size, lattice strain, density of the dislocation, and variation of the lattice parameters. The hot pressing technique causes the powder particle to refine the grains and the difference in the structural parameters. So the X-ray diffraction analysis, here you can show here 0 hours, this 5 hour sample, 10 hour, 15 hour and 20 hour samples of this aluminum 7017 alloys. So here these samples, while increasing the milling hours, the intensity of peak is broadened due to the refinement of the grain size as compared to the sharp peak in the as-received powders. This is the as-received powders, 45 micron size, 325 size. This is the below 15 nanometers, so that the intensity of the peak is reduced and the peak width is increased. And also the precipitate also formed during the mechanical alloying process, like MgZn2, because the magnesium and zinc is diffused into the aluminum alloys. In the left hand side shows the enlarged views of this X-ray diffraction of the powders. This is the hot pressed compaction of this aluminum 7075 alloy. It's also indicate the MgZn2 precipitate will be formed in the 20 hours milled powders due to the refinement of the grains. So this is the estimation of the crystal size, like Williamson-Hall methods. Crystal size, we followed the three methods by using the numerical equations like Scherrer equation, Williamson-Hall method, modified Williamson-Hall method like uniform deformation model, uniform stress deformation model, and uniform density energy deformation model. We calculate the four models. As the milling time increases in all the models, the crystal size is decreased in the powders powders. While in the hot pressed, in the red color shows the hot pressed samples, the milling hours increases, the crystal size is little bit increased due to the particle diffusion, interparticle diffusion, the grain growth occurred. As the milling hours increases, the crystal size was reduced. Due to the refinement of grain size in the all the models, we calculated based on the numerical equations. So estimation of the lattice strain for the Williamson modified Hall methods, we followed the uniform deformation model, uniform stress deformation model, uniform density energy deformation model. We calculated as the milling tower increases, the lattice strain is increased due to the repeated cold welding, fracturing, and severe plastic deformation of these particles. As the milling hours increases, the lattice strain also increased in the all the three models. So estimation of this estimation of the lattice strain dislocation density of the different models, modified Williamson Hall methods. As the milling hours increases, the dislocation density also increases due to the structural refinement of these powder particles, and also the diffusion of these metal particles. So the XRD graph of this lattice parameter and percentage of changes in the lattice parameters. As the milling hours increases, the lattice parameters was decreased due to the refinement of grains, and also the repeated welding, cold fracturing, deformation, and severe plastic deformation of these particles, and also the diffused the hot pressed samples in the hot pressed conditions at the processing temperatures. So the powder surface morphology evaluation, the purpose of the study is using the high resolution scanning electron microscope and high resolution transmission electron microscope, reduction in particle size and changes in the particle shape during the mechanical alloying, the some microstructure of the hot pressed sample, then the bright field, dark field, selected area, electron diffraction pattern, and lattice fringes of the powder samples, eta and eta precipitate formed in the hot pressed samples using the high resolution transmission electron microscope analysis. So this is the microstructures of the high resolution scanning electron microscope of this 0 hour. This is insert shows the higher magnification. You can see here the powder particles are in spherical shape, some flat and irregular shape. As the milling hours increases from 5 hour, 10 hour, 15 and 20 hours, the particle size was reduced. So that we are converting the particles from micron level to nano level. This is the microstructure of the hot pressed samples. This initial hot pressure samples of the bulk samples. The initial one shows these the grain size, coarse grains, and also some pores also there as compared to 5 hour and 10 hour. If the 20 hours, we will get the fine grains, fine grains compared to the coarse grains due to the refinement of the grain size, refinement of the grain size. The advantages of this hot pressing technique is we are simultaneously we are applying the pressure and we are applying the temperature, so that the pores will be reduced as compared to the conventional sintering process. So this is the powder particles of this initial powders, 5 hour powders. This is the bright field image. This is the dark field image. This is selected area diffraction. This is the lattice fringes. This as the milling hours increases, the particle size was decreased as we are going for the high resolution transmission electron microscope as compared to the high resolution scanning electron microscope. The higher magnifications, so we'll get the continuous rings of these nanocrystalline structures. And also this clearly indicates this during the mechanical alloying process, the precipitate will be formed, MgZ and precipitate will be also formed during the mechanical alloying process. You can see the high resolution transmission electron microstructure of the hot pressed samples. So the in the hot pressed samples, you can see the as received samples, eta and eta primes, as we compared into the 20-hour samples in the 100 nanometers, very fine precipitate and Mg set into precipitate also formed. So this indicates the improvements of this mechanical properties of these materials as compared to the 0-hour and blended samples and 20-hour samples. And also it indicates the continuous ring patterns of these structures. So this is the differential scanning colorimetry. This initial and final, it indicates the formation and GP zones and dissolutions and formation of supersaturated solid solution, which indicates this temperature in the endothermic and exothermic. So it indicates this the precipitate formation will be formed. The mechanical behavior of these hot pressed samples. The purpose of the study is to investigate the effect of milling time duration on Vickers microhardness and compressive strength of the hot pressed samples, to examine on the cause of the material failure through the SEM analysis, to study on the various strengthening mechanisms such as solid solution, grain boundary strengthening, dissociation, precipitation strengthening, and R1 strengthening. We calculated based on the numerical equations. As the milling hours increases, the hardness value also improved from initial 120 to the 240 VH and Vickers micro hardness values. Here we are applied load of 200 grams and 12 time of 10 seconds. This diagram shows the hot pressed compressive strength of the samples as the compared to 0 hours. The 10 hours milled samples shows the higher strength as compared to the 20 hours milled sample, because in 20 hours samples they have we are increasing the milling hours, they have more in brittle nature, as so that the hardness value is improved, but the compressive strength was decreased. So this is the microstructure of this spectrography of the compressed samples, initially intergranular cracking in the 0 hours, and some dimples and voids cleavage facets also we can see in the micrograph. We can see in the 20-hour sample some brittle fracture also occurred during this compression testing process as compared to the 0-hour samples. So this is the strengthening mechanism we calculated based on the numerical equation: grain boundary strengthening, precipitate strengthening, solid solution strengthening, and dislocation strengthening based on this 20 hours. Based on the milling times we calculated, as the milling hours increases, the strength of the materials also have been improved. The conclusion of this alloy only will alloy. Mechanical alloying effectively established a nanocrystalline aluminum 7017 alloy with different milling time duration. After 20 hours of milling, a steady state was achieved during the milling. So that we stopped up to the 20 hours with the formation of equioxed spherical particles, and EDS revealed that the nanocrystalline powders were tamed. The powders were consistently disseminated, which was assigned the HRTM and as a nanocrystalline of 70 nanometer was accomplished with 20 hours milling. Furthermore, the formation of nano grain size MGZ and precipitate during the mechanical alloying was detected in the high resolution transmission electron microscope. It will give the clear indication of this micrograph. This XRD peak broadening of the milled powder and hot pressed samples uh, hot pressed samples and observed that the dislocation strengthening being the dominant mechanism, followed by the solid solution and precipitation and grain boundary strengthening. So the next one is as per till now we discussed about only the matrix materials. Then we are mixed with the 10 volume percentage of the aluminum oxide composite material, the same prepared by the mechanical alloying and hot pressing samples. We characterize the initial powder and final powders. Then the particle size was reduced up to 23.51 nanometers. So the XRD pattern as the function of the milling time in the composites in the aluminum 7017 alloy plus 10 volume percentage Al₂O₃ composites. So that the aluminum based solid solutions with the Al₂O₃ and MgZ12 formation of these structures, and also as the milling hours increases, the peak intensity will be broadened and the peak intensity also will be reduced. It indicates the nanocrystalline nature of these materials. And also the XRD graph of the hot pressed samples, aluminum 7017 alloy, the 10 volume percentage of Al₂O₃ composites. The peak shifts indicate this refinement of this grain size of this composite samples. This is again we calculated based on the estimation of the crystal size and the hot pressed samples like Scherer UDM model, uniform deformation model, uniform stress deformation model, uniform density energy deformation model. We calculated as the milling hour increases, the crystal size was reduced in all the models. Then we calculated based on these composites, again we calculated the lattice strain. As the milling hours increases, the lattice strain also increased in the powder as well as in the compacted samples. As compared to the powder samples, the compacted samples have more lattice strain due to the strain hardening of these materials. This is the dislocation density of these materials. As the milling time increases, the dislocation density also increased for all the three models due to the cold welding, fracturing, and fragmentation of the particles. We can see the powder morphology of this high resolution scanning electron microscope of this initial composite and you can 5-hour composite, 10-hour, 15-hour, and 20-hour composites. As the initial powders, the particles are flake like irregular morphologies. When comparing to this 20 hours milled powders have some spherical shape and particle size was also reduced. It is the evident that the particle size was reduced. We can go for the high resolution transmission electron microscope. We can show the nanoparticles, and also we can see in the hot pressed sample composites, they have the initial one, the coarse Al₂O₃ particles, and also the particles are agglomerated in the initial blended condition. We can go for the 5-hour and 10 hours. The particles are uniformly dispersed as compared to the 5-hour, 10-hour, 15-hour, 20 hours have uniformly dispersed and have some more precipitate also formed during these hot pressing techniques. So this high resolution transmission electron microscope clearly indicates the bright field image and dark field image indicates this particle size have the how in 50 nanometer the particle size are nanoparticles. Also it indicates clearly shows the nanocrystalline, the ring pattern clearly shows the nanocrystalline nature of this materials. So we attained the nanocrystalline nature of the composite powders. So you can indicate this hot pressed compacted of this high resolution transmission electron microscope images. So these images shows micrograph images shows the evident that this continuous ring pattern also shows, and also we'll get the nanocrystalline nature of this material, and also the MgZ2 and the composites also formed during this hot pressing technique. This is the direct evidence of this micrograph indicates the strength of these materials. So, and also we calculated, we performed the DSE and also the formation of GP zones and supersaturated solid solution of this endothermic and exothermic pumps. We can able to see this DSE. And also the mechanical behavior of these hot pressed samples, we can show the milling hours increases, the hardness values also increase. This composite with the 10 volume percentage. We can see here the compressed test samples with the different hours we calculated. It indicates this green one shows more brittle in nature as compared to this 10-hour samples. So this is the factorograph images of this composites indicates the intergranular crack and also some river pattern in the 20-hour samples and also the crack growth direction. Here is the 20-hour sample shows some stumbles, some voids also. We can indicate some the things. This the conclusion of this overall things we can see about this XRD will get the mean particle size of 16.38 nanometers and also the structural changes during this mechanical alloying process, and also the hardness values also improved during this composites. So the next one is the similar way we followed the yttrium oxides composite prepared by the same technique. We can able to see the particle size of these materials, and also we can able to see the XRD graph of this powder particles also with the aluminum based solid solution of the yttrium oxide. We can also able to see this compared to the initial one and final one will get the nanocrystalline nature. Also this is shows the hot pressed samples of this yttrium oxide samples. We can show the nanocrystalline nature. This is the structural parameters we calculated based on this modified Williams and Hall methods and also structural parameters of nanocomposite Williams and Hall method, this crystal size, lattice strain, and also dislocation density also we followed. So we followed by the high resolution scanning microscope images of this initial powders and final powders. We can compare to this initial and final, we'll get the more fine particles. You can see clearly, you can see in the hot pressed samples, we are having the more coarse grains and also some agglomerated coarse particles also formed as compared to the 20 hours samples composites, the nanograins of Y₂O₃ particles also we can see. You can see the high resolution transmission electron microscope in the initial one and final one will get more fine nanoparticles of this yttrium oxide nanocomposite. When going for this bulk samples, high resolution transmission electron microscopes images, the nanocomposite, the hot pressed samples, it clearly shows the eta frame of MgZ and precipitate as compared to the initial one, the initial one, 20 nanometers. We are comparing this is will get the fine nanocrystalline nature. This is the DSE curve of this formation and dissolution of supersaturated solid solution and mechanical behavior of the hot pressed samples for the this composites. We can indicate the milling hours increases, the hardness values also improved, and also the 10-hour sample shows the more ductility as compared to the 20-hour samples have the more brittle nature. So that you can see here this brittle in nature as compared to the 10 hours and 15 hours, some voids, some minor cracks and timbers also formed during the compression testing process. This is the strengthening mechanism of this particular composite. We have achieved this 20 hours. And also this is the conclusion of this composite, yttrium oxide composite. We have achieved this high resolution of transmission electron microscope for this 18.9 nanometers and the particle size with the particle size of mean particle size of 16.23 nanometer we found in the high resolution transmission electron microscope, and also we can able to see the hardness values improved from 260 to 906.45 megapascal we achieved in this composite. Coming to this final hybrid composites, we blended with 5 volume percentage of Al₂O₃ and 5 volume percentage of Y₂O₃ hybrid nano composite prepared by the mechanical alloy and 40% techniques. This is the hybrid composites. You can show the initial one and the final one. It shows this hybrid composites of this particular aluminum based solid solution will got these results. And also with this is the hot brushed nano composites of nanocrystalline nature of this material. Also we got the hybrid composites. And also this is the crystal size of this hybrid composites we calculated based on this Scherer and modified Williamson Hall methods. And this is the lattice strain of this hybrid composite calculated. As the milling hours increases, lattice strain also increases. This is the lattice parameter and stacking fault probability of these materials we calculated. This is the initial hybrid composite powders, and this is the 20-hour milled powder composite powders. The particle size was reduced during the mechanical alloying process. This is the initial one. This is the hybrid nano composites, the blended powder sample. This is the 20 hours build samples. We can clearly shows the nanocrystalline structure. You can see in the high resolution transmission electron microscope images, as it indicate that clearly it shows the nanocrystalline nature of this selected area lattice fringes. Also we can able to see in this microstructure. This is the 20 hours milled powders. Shows the lattice fringes, and also we can source the bright field image and dark field image. It indicates the particle size was reduced in nanocrystalline nature and also in nanometer range. So this is the high resolution transmission electron image of this hybrid composites, hybrid composite. The sample preparation was, this is not easy job. This is a very tough job to prepare this high resolution transmission electron microscope. We prepared the sample for 10 mm diameter, 5 mm height. But we have to take this microstructure, we have to prepare, we have to reduce the below 100 microns, so that only we can able to get this microstructure. So this is the very tedious process to prepare this high resolution transmission electron microscope, so that we got the good results from this, how this nanocrystalline nature of this material, the hybrid composite, was formed during the mechanical alloying process followed by the hot pressing techniques. So we got the good mechanical properties. This is the direct evidence of this micrograph. So this is we did the DSC curve of this hybrid composites. Then we followed the mechanical properties of the hardness values and compression test. Then we followed by the compression test. We took the factorographic, some technical terms, these voids, some minor cracks also we can able to see in the 20 hours. You can see the micrograph why the ductile material to the brittle material, how it will be transition occurred. It will clearly indicates this microstructures. This is the conclusion of this overall conclusion of this hybrid composites. As the milling hours increases, the grain size will get the nanocrystalline nature. So this is the some publication of our journals, and this is the things. These are some literature survey. Thank you. You have any questions?
Thank you, sir. Thank you for a valuable presentation.